Usually when we think about building a physical structure, there's this expectation of precision and stability just built right into the blueprints. Like you put up a steel beam, you calculate the exact load, and the structural engineer just points to the math and says, well, that beam holds the roof.
Right. Yeah, it's physics, it's predictable, it's totally binary.
Exactly.
The beam is either standing or it's falling. We really like physical forces to be governed by unbreakable laws that, completely ignore human feelings.
Yeah, but then you step into the world of human interaction, the world of like strategic competition, negotiations, warfare, whatever, and suddenly that structural blueprint is completely useless.
Oh, absolutely.
Because you're no longer dealing with dead steel, right?
Right.
You're dealing with a behavioral landscape where every single beam is actively moving based on what it thinks the other beams are doing.
Which is just the absolute definition of strategic chaos. Every decision rests on another decision.
Right.
And that rests on another decision.
Right.
Endlessly.
And today, we're going to look at how we finally managed to, put a mathematical cage around that chaos. Our mission in this deep dive is to explore a really specific, honestly, incredibly dense set of source materials that you provided for us.
Yeah, it's a lot to get through.
It really is. It's all centered around a paper titled Nash Equilibrium, a mathematical foundation. And we are going to extract the absolute core insights from this text, the mathematical blueprints, the behavioral quirks of how humans actually act, and even the evolutionary realities that are hidden inside this work.
And we should probably set expectations right away for you listening. This material does not hold back. I mean, we are looking at a topic that spans an astonishing range of disciplines.
Oh, yeah.
We're talking about algebraic topology, the intricacies of computational complexity, and, well, believe it or not, the violent mating habits of the muskox.
Yeah, the muskox definitely caught me off guard when I was reading through the notes. But, that is the exact goal of this deep dive. We want to be your shortcut to being genuinely well-informed on this topic.
Right.
We're going to explore how a young mathematician, John Nash, proved something so profound, so deeply foundational to human interaction, that the greatest mind of his time literally dismissed it as trivial.
Which is just crazy to think about now.
It really is. Yet that so-called trivial proof went on to explain everything from, global nuclear brinkmanship to the biological evolution of animal horns. So, all right, let's unpack this. Because game theory didn't just start with John Nash, right?
No, it didn't. To really appreciate the magnitude of what John Nash achieved in 1950, we first have to understand the boundaries of the world he was working in. We have to look at the state of game theory before he even arrived on the scene.
Setting the stage.
Exactly. And back then, game theory was heavily constrained by the structural foundation laid by two absolute giants in the field, John von Neumann and Oskar Morgenstern.
Right, John von Neumann. I mean, you really can't overstate how important this guy was. He was a towering figure in mathematics, physics, computer science, you name it.
Oh, he was a genius.
But according to our source text, his framework for game theory was built around a very specific, almost paranoid paradigm, the classical two-person zero-sum game.
Yeah, paranoid is the perfect word for it. Von Neumann's world was strictly adversarial. And we should probably break down zero-sum, because we hear that term thrown around a lot in, business meetings and political debates.
Yeah, it's become a bit of a corporate buzzword.
Right. But in this formal mathematical context, it means something very rigid.
So it's not just a fancy way of saying someone loses.
Exactly. A strict zero-sum game means the total amount of utility. So the score, the money, the resources is completely fixed. There's no creating new value. The interests of the two players are diametrically opposed.
So one player's gain is invariably exactly the other player's loss.
Exactly. If I win $5, it is only because you lost $5. And von Neumann successfully solved these types of games using a mathematical concept called minimax optimization.
Minimax, so essentially minimizing your maximum possible loss.
Correct. The logic goes like this. You have to assume that your opponent is out to completely destroy you. Because mathematically, that is their only path to victory. Their win is your loss.
Wow. So it really is a paranoid way to look at the world.
It totally is. So you play entirely defensively to guarantee the best possible worst-case scenario for yourself. You expect the absolute worst from the other guy, and you optimize for it.
I mean, it's an elegant mathematical solution, but it describes a very dark, purely adversarial world. And the source text points out that the real problem arises when you try to expand that logic outside of a simple two-player deathmatch.
Right, because the real world isn't always a deathmatch.
Exactly. What happens when you have three players? Or 100 players? Or, what happens when a game just isn't zero-sum? What if there's a possibility for mutual benefit, like trade, or mutual destruction, like nuclear war?
Well, that was the wall that von Neumann hit when he tried to extend his theories to those more complex scenarios. To more than 2 players, he got really bogged down. To make the math work, his cooperative extensions relied on these incredibly complex and frankly unrealistic assumptions about how people coordinate.
Yeah, the text mentions coalitional coordination.
Yes. Von Neumann essentially assumed that players would just naturally form binding coalitions. He built his math on the idea that they would sit down, communicate openly, make binding contracts, and perfectly share resources or divide the spoils to maximize the group's total payoff.
But that doesn't mirror the real world at all. In the real world, contracts are broken. People lie.
Yeah, or they just act selfishly.
Right. Or in a lot of situations, players can't even communicate with each other at all. You can't just assume everyone is going to sit in a circle and perfectly divide the pie.
Right.
And that flawed assumption is the exact paradigm that John Nash shattered, isn't it?
It really is. Nash made this massive intellectual leap. He completely shifted the analytical focus away from von Neumann's coalitional agreements and moved it to a concept called strategic independence.
Strategic independence.
Yeah, what's fascinating here is how Nash redefined the basic parameters of the game itself. He didn't just tweak von Neumann's work, he completely bypassed it. He formulated a generalized, non-cooperative equilibrium concept.
Let's hover on that word for a second. Non-cooperative. That really feels like the key to the whole thing.
Yeah.
He basically said, let's build a model that assumes no one is talking, no explicit communication, no binding contracts.
Right, no guaranteed collaboration at all.
Every single participant is acting entirely independently, purely in their own self-interest.
And critically, his new framework wasn't just limited to 2 players either. It applied to any finite number of players. And it didn't matter if the game was zero-sum or non-zero-sum. It was a universal blueprint.
And the absolute core of this universal blueprint is what we now call the Nash Equilibrium. The text defines it as characterizing a state of strategic stability. I really want to pin that down for you listening. What does a state of strategic stability actually look like? Like, if I'm playing a game, how do I know I've reached the Nash Equilibrium?
You know you've reached it when no one has any regrets.
Oh, I like that. No regrets.
Yeah, the formal definition is that it's a specific profile of choices, like a snapshot of the state of play, where absolutely no player can unilaterally deviate to improve their expected payoff, given that all the other players maintain their chosen strategies.
Okay, unilaterally, meaning on my own. So I can't look at the boards, see what everyone else is doing, change only my move, and get a better score.
Exactly.
If everyone else is playing their Nash Equilibrium strategy, my Nash Equilibrium strategy is the absolute best possible response to them. I might not be totally happy with my score, but any other move I make right now would only make it worse.
Right, you're locked in.
We are all locked in a perfectly balanced tension.
And that specific tension, that mathematical guarantee of stability, is what bridged entirely different fields of mathematics. The source text really emphasizes that Nash's foundational concept brought together mathematical optimization, algebraic topology, and computational complexity.
It's massive.
It is. He took game theory from being a niche study of zero-sum parlor games like poker or chess and transformed it into a rigorous universal discipline that could analyze literally any human interaction.
It's just an incredible achievement, but I think to really grasp how he proved that this magical balanced tension always exists, we need to get our hands dirty with the actual mechanics.
Yeah, we have to look at the math.
Right. We need to transition from the history of game theory into the formal mathematical blueprint of a game itself. Like, how do we actually build this cage?
Well, we start by looking at the formal mathematical formulation of strategic equilibria. In the text, this begins by defining a game in its normal form. Sometimes this is also called the strategic form.
Now, the text uses a bunch of mathematical notation here, tuples and variables. But for you listening, don't worry. We're not going to just read equations at you. Let's translate this into plain English. To mathematically define any game, you basically just need 3 basic ingredients, right?
Yes. It's a really elegant way to compress the infinite complexity of human interaction into a simple list. The first ingredient is the players. The text denotes this with an N. This is just the finite set of people involved.
Okay.
It could be 2 people, it could be 1,000,000 people, but it has to be a concrete finite number.
Okay, so ingredient 1 is who is playing. Ingredient 2.
The actions they can take. The text calls this the finite set of pure strategies specific to each player. Think of these as the distinct, concrete choices available to you.
Give me an example.
So if you're playing chess, a pure strategy would technically be a complete deterministic rulebook for exactly what you will do in every possible board state.
Whoa. So a pure strategy means there's absolutely no hesitation. I'm doing X, period.
Exactly. No randomness. And the third and final ingredient is the utility, or the payoff function.
The scorekeeper.
Right, the scorekeeper. It takes the combination of every pure strategy chosen by every player, looks at how they collide, and assigns a final score, a real number, to each player. It tells you exactly how much benefit you get when your action interacts with everyone else's actions.
So we have the players, we have their concrete deterministic actions, and we have the score. I mean, that seems pretty comprehensive.
It does, but
The text introduces a massive structural flaw right here, doesn't it? If we only rely on those pure strategies, those deterministic 100% committed actions, the whole system breaks down in a huge number of scenarios.
yeah, there is no stability.
What?
It definitely breaks down. The text points out that while some games do possess pure strategy equilibria, many very common, very simple games absolutely do not.
And the classic example provided in the text is rock, paper, scissors, which I think is the perfect way to understand why pure strategies fail.
Oh, absolutely.
Let's say we're playing, and you decide before the game that your deterministic pure strategy is going to be rock. You are going to play rock 100% of the time. What happens?
Well, I get destroyed.
Yeah.
You figure it out instantly. You observe my pure strategy, and you exploit it by playing paper 100% of the time. I am completely exposed because I am entirely predictable.
Right. And then once you realize I'm exploiting you with paper, you unilaterally deviate. You switch your pure strategy to scissors.
And then you see that,
Yeah.
and you switch your pure strategy to rock.
And we just chase each other around this triangle forever. You get stuck in this continuous loop of best responses. At no point in that cycle is there a Nash equilibrium. There is never a single moment where neither of us wants to change our move. We always want to deviate.
Precisely. If you restrict the mathematical universe to only pure strategies, a Nash equilibrium simply doesn't exist in a game like rock, paper, scissors. The cage is empty. So, to guarantee the existence of an equilibrium, Nash realized that the strategy space itself had to be fundamentally expanded. We have to move away from pure strategies and introduce what are called mixed strategies.
This is where we bring in the element of surprise. Probability. A mixed strategy allows players to randomize their choices according to a specific probability distribution.
Yeah, the formal definition in the text is that a mixed strategy is a probability distribution over a player's available pure strategies. You aren't just choosing an action, you are choosing the percentages of how often you play each action.
Okay, the text uses some very dense geometric language here. It talks about standard simplices and mathematical spaces. But I want to avoid textbook jargon here. Let's try to visualize this for the listener.
Sure.
If a pure strategy is just a single point, like a single dot on a piece of paper, a mixed strategy is like an entire physical control panel.
I like that. Let's explore that analogy.
Think of a mixed strategy like a DJ's audio mixing board. You have 3 volume sliders labeled rock, paper, and scissors. If you push the rock slider all the way up to maximum volume and leave the others at 0, well, that is a pure strategy. You're playing rock 100% of the time.
Right.
But a mixed strategy means you can set those sliders anywhere you want. You could slide rock to 30%, paper to 30%, and scissors to 40%.
And that specific configuration of the sliders, that exact blend of percentages, represents one single mixed strategy. It is a coordinate in the mathematical space, and the text outlines 2 absolute unbreakable laws for this mixing board.
Right, the physical limits of the board, what are they?
First, every slider must be set to a value greater than or equal to 0. You cannot play rock negative 20% of the time. That just breaks the laws of probability.
Makes sense. You can't have negative volume. Got it. And the second law?
The sum of all the sliders must equal exactly 100%.
Yeah.
If you move the rock slider up, one of the other sliders must move down. You have to play something exactly 100% of the time.
So any combination of sliders that adds up to 100 is a valid mixed strategy.
Yes.
And what's interesting is how the text redefines a pure strategy once this board is introduced. It calls a pure strategy a degenerate mixed strategy.
Yeah, it's just mathematical terminology. It just means a mixed strategy pushed all the way to its absolute extreme.
Yeah.
One slider's at 100% and the others are at 0.
Okay, so that's my mixing board. But a game has multiple players. We all have our own boards. How do we mathematically combine everyone's randomizations together?
The text calls this the joint mixed strategy space. Mathematically, it is constructed using a Cartesian product.
Okay, pause. Cartesian product. We promise no undefined jargon. What does that actually mean for our DJ boards?
Fair point, fair point. A Cartesian product simply means taking every possible setting on your mixing board and pairing it with every possible setting on my mixing board and every possible setting on a third player's mixing board, and so on.
Okay.
It multiplies all the individual possibilities together to create one massive, multi-dimensional menu of every single combination of strategies that could possibly exist in the game.
It's like the master control room.
Exactly. And the text notes that because of how we built this master control room, no negative probabilities, everything adding up to 100%, this joint space inherits some very specific geometric properties. It says the space is compact, closed, bounded, and convex.
Compact, closed, bounded, convex. We will definitely need to unpack those specific topological properties later when we get to how Nash actually proved his theory. But for now, just understand that this master space contains every possible probabilistic reality of the game. But wait, if everything is just percentages and chances now, how do I know if I'm winning? Like, how do you calculate a score when the actions haven't even been locked in yet?
You calculate the expected payoff. It's basically a weighted average. You look at every possible pure outcome that could happen, you multiply the score of that outcome by the probability of that outcome actually occurring based on everyone's slider settings, and then you add all those numbers together.
Okay, so it's like calculating the expected return on a really complicated investment portfolio. You don't know exactly what the market will do on any given day, but based on the probabilities, you can calculate your expected average return over time.
Exactly. And this expected payoff calculation relies on a massive assumption about human psychology that the text calls classical rationality.
Classical rationality, which implies humans are just cold calculating machines.
Yeah, pretty much. It assumes that player choices are guided by a strictly consistent preference relation over different lotteries, governed by something called the independence axiom.
Okay, break down the independence axiom for me.
It means your preferences shouldn't be altered by irrelevant alternatives. Let's say you strongly prefer a slice of apple pie over a slice of cherry pie.
True statement.
Okay, good. Now, I offer you a gamble, a coin flip where heads gets you the apple pie and tails gets you a completely unrelated prize, say a new car.
I mean, yeah, I'm taking that coin flip.
Right. Now, what if I offer you a second coin flip? Heads gets you the cherry pie, and tails gets you the exact same new car. The independence axiom states that because you prefer apple over cherry, you must strictly prefer the first coin flip over the second one.
Because the car is in both.
Right. The introduction of the car, which is identical in both scenarios, should not mathematically alter your baseline preference between the pies.
So you have to act logically consistent under risk.
Yes.
And because we assume players are acting logically to maximize their expected payoff, the text arrives at a really critical threshold in Nash's framework. It says a mixed strategy is only a best response if you assign positive probability only to the pure strategies that tie for the absolute maximum expected utility.
Right. And let's explain why that is. Since the expected payoff calculation is just a linear average, if one pure strategy gives you an expected payoff of 5 and another gives you an expected payoff of 10, why would you ever assign any probability to the 5?
You wouldn't. Every percentage point you assign to the 5 just drags your total average down.
Precisely. Therefore, the text states a profound rule. If you are mixing between multiple strategies, you must be completely indifferent between them. They must all yield the exact same maximum expected payoff. Any pure strategy that yields even a fraction of a point less than the maximum must be played with exactly 0 probability. You just dropped it completely.
That actually blew my mind when I read it. Let's look at how this actually plays out when trying to solve a game, because this is where the logic feels totally backward. The text provides a coordination game called the Battle of the Sexes.
Yes.
Walk me through the mind-bending logic of finding the Nash equilibrium here.
Well, in a mixed strategy game, you don't actually look at your own payoffs to decide your probabilities.
Which sounds completely wrong. My whole goal is to maximize my own score.
I know. But if you just chase your own maximum score, you end up in the endless loop of rock, paper, scissors. The genius of the Nash equilibrium is that you look at the game entirely from your opponent's perspective.
Wow. So you have to set the sliders on your mixing board specifically to render your opponent completely indifferent between their options.
Yes. You mathematically manipulate your own randomness to paralyze your opponent. Let's say you are choosing between option A and option B. You set your probability percentages so that no matter whether your opponent chooses their option X or their option Y, their expected payoff is exactly the same.
And if their expected payoff for X is identical to their expected payoff for Y, they have no mathematical incentive to switch. They are stuck.
Exactly. And while you are doing that to them, they are doing the exact same thing in reverse to you. They are setting their probabilities to make you indifferent between A and B.
So we are both simultaneously neutralizing each other's incentive to deviate. We are trapping each other in a mathematical stalemate using probability. That self-confirming loop of best responses is the essence of a mixed strategy Nash equilibrium.
It is brilliantly counterintuitive.
It really is. So we have the sterile math, we understand the mixing boards and the probabilities, but the source text doesn't stop with just the abstract theory.
No, it goes much further.
It moves into how this math actually collides with reality. It transitions into a menagerie of games, exploring the tension between cold rational math and, quite frankly, irrational humans.
Yeah, the text provides a very detailed payoff matrix detailing 4 specific archetypal games. Each one is designed to highlight a different facet of strategic dynamics and show how the Nash equilibrium behaves in different environments.
The first one is a game we've kind of already touched on, matching pennies.
Right. Structurally, matching pennies is basically the 2-option version of rock, paper, scissors. 2 players each secretly choose heads or tails and reveal them simultaneously. If the coins match both heads or both tails, player 1 wins player 2's penny. If they don't match, player 2 wins player 1's penny.
So it is strictly zero-sum. My win is your loss. And just like rock, paper, scissors, there is no pure strategy equilibrium here. If I know you're playing heads, I play tails. Then you switch to tails, and we just chase each other forever.
So we had to use mixed strategies. And because the game is perfectly symmetrical, the only way to make your opponent mathematically indifferent to their choices is to randomize with a strict probability of 0.5, a 50-50 coin flip.
Right.
If I play heads exactly half the time, it doesn't matter what you do, your expected payoff is 0. It's the only point of stability.
Simple enough. But the text immediately ramps up the stakes with the second game in the table, the prisoner's dilemma. I mean, this is arguably the most famous game in all of economics.
And for good reason. It perfectly illustrates the tragic flaw of rational self-interest. Unlike matching pennies, the prisoner's dilemma is a non-zero-sum game. The total amount of utility can change. There is a possibility for mutual benefit, but the mathematical logic actively destroys it.
Right. Let's set it up for anyone who hasn't heard it. We are both arrested for a crime. We are in separate interrogation rooms. We can either choose to cooperate with each other, meaning we both stay silent, or we can defect, meaning we snitch on the other person to the cops.
And mathematically speaking, the tragedy here is that defection is what the text calls a strictly dominant strategy.
Let's explain that. A strictly dominant strategy means that no matter what you do, it is always in my mathematical best interest to play this move.
Exactly. Let's run the numbers. If you choose to stay silent, to cooperate, I can either stay silent too and we both get a light 1-year sentence, or I can snitch on you, defect, make a deal, and walk out totally free while you get 10 years. 0 years is obviously better than 1 year, so if you cooperate, I should defect.
But what if I snitch on you? What if I defect?
Well, if you snitch on me, I can either stay silent and get the full 10 years, or I can also snitch and we both get 5 years. 5 years is better than 10 years. So if you defect, I should still defect.
Regardless of what I do, you are always better off defecting.
Yes.
So the unique Nash equilibrium, the only stable point where neither of us wants to change our move, is mutual defection. We both snitch. We both get 5 years.
But the critical, heartbreaking observation the text makes here is that this unique Nash equilibrium is mathematically Pareto-dominated by mutual cooperation.
Pareto-dominated. That means there is another state on the board where everyone would be strictly better off. If we had just both stayed silent, we would have only gotten 1 year each. The mutual cooperation outcome yields significantly higher utility for both of us than the Nash equilibrium outcome.
Yes, but because of strategic independence, because we are in separate rooms and cannot form a binding, enforceable contract, the cold logic of rationality forces us both into a worse outcome. We rationally optimize our way into a worse reality.
It perfectly illustrates why von Neumann's assumption that people will just naturally coordinate for the best mutual benefit is deeply flawed.
Exactly.
Okay, the third game in the menagerie takes that tragedy and turns it into terror. The chicken game.
Oh, the chicken game. This is another symmetric non-zero-sum game, but instead of modeling cooperation, it models brinkmanship. 2 drivers are speeding straight at each other on a narrow road. You can choose to retreat, swerve out of the way, or issue an ultimatum. Keep driving straight.
The stakes here aren't jail time, they're life and death. And the text points out that this game actually has multiple equilibria. It has two pure strategy equilibria. One driver swerves, looking like a coward, and the other drives straight, looking like a hero.
Right. If I swerve, you have no incentive to swerve, so you go straight. If I go straight, you absolutely have an incentive to swerve so you don't die. Those are stable states.
It also has one symmetric mixed strategy equilibrium where you both randomly decide whether to swerve or stay straight based on a specific probability. But the absolute terror of the chicken game is that double defection, where both players independently choose the ultimatum action, yields a catastrophic utility.
They crash. They die.
The math literally includes the possibility of utter annihilation as a valid calculating component of the strategic landscape, which perfectly models the logic of nuclear deterrence during the Cold War.
It's terrifying, really. Which brings us to the final game in the text table. And this one is perhaps the most revealing when it comes to actual human behavior. The traveler's dilemma.
I love the traveler's dilemma because it creates this massive collision between perfect math and actual human psychology. The setup is this. Two travelers have identical valuable luggage lost by an airline. The airline manager puts them in separate rooms and tells them to write down the value of the luggage, claiming any dollar amount between $2 and $100.
Right, but there's a very specific penalty parameter attached to the payout. If both travelers write down the exact same number, the airline assumes they are telling the truth and pays them both that amount.
Okay.
But if they write down different numbers, the airline assumes the person claiming the lower number is being honest. The airline pays both travelers the lower amount, but it subtracts a $2 penalty from the person who claimed higher and adds a $2 reward to the person who claimed lower.
Okay, let's play this out. I want to maximize my money. I think the luggage was worth $100. I'm going to write down $100.
Well, the logical deduction here is brutal. If I think you're going to claim $100, I shouldn't claim $100. I should claim $99. Because if I claim $99, the airline pays us both based on the $99. But I get a $2 reward, so I walk away with $101. And you get penalized, so you walk away with $97. By undercutting you by just $1, I make more money than if we had tied at $100.
But wait, I'm a rational actor. I know you're going to try and undercut me to 99. So knowing that, I'm going to unilaterally deviate. I'm going to claim 98. That way, the payout is 98, but I get the reward, making it 100, and you drop to 96.
And since I know you know that I know, I will claim 97.
And it unravels all the way down to the absolute bottom.
He really does.
The text explicitly states that the unique Nash equilibrium for the traveler's dilemma, the only state where neither of us can profitably undercut the other, is for both of us to claim the absolute minimum possible amount. $2.
The math dictates that $2 is the only perfectly rational, stable outcome.
Okay, I have to push back here. I have to challenge this. The text admits that when economists actually run this experiment with real human subjects, they don't play $2.
No, they don't.
They consistently claim amounts in the high 90s, especially when the penalty is low. And here's the thing. Those humans walk away with significantly more money than the rational mathematicians who play $2. If the math dictates an outcome that leaves me poorer in reality, isn't the math just wrong?
It's a fantastic question, and it highlights a crucial misunderstanding of what game theory is. It's not a matter of the math being wrong, it's a matter of what the math is defining. The Nash Equilibrium defines strict classical rationality. It assumes a cold prescriptive logic based on infinite recursion. I know that you know that I know that you know down to infinity.
But humans physically can't compute infinite recursion. We get tired, we trust each other, we have a general sense of fairness or at least a heuristic desire to not blow up a good deal.
Exactly. Real humans are driven by complex, messy psychological factors. When real people play the traveler's dilemma, they usually recognize the logical trap after 2 or 3 steps of undercutting, and they just stop. They jump to a good enough cooperative outcome, say $95, rather than logically spiraling themselves all the way down to a $2 payout.
So humans are irrational, but in this case, being irrational is actually more profitable. But doesn't that behavioral divergence weaken Nash's whole theory? Like, if people don't actually act like the Nash equilibrium predicts, why does it matter?
It matters precisely because human behavior is so chaotic. This is the crucial point. You cannot prove a universal foundational law of strategic stability by simply observing human beings.
You can't just watch a group of people play a game and say, well, they settled on $95, so $95 must be the mathematical law of equilibrium.
Because a different group of people in a different mood might settle on $40.
Right.
Precisely. Humans are heavily reliant on cultural context, emotion, and cognitive limits. If Nash had tried to prove his theory empirically, by running experiments and recording data, it would have failed instantly because human data is noisy and inconsistent. To prove that stability must exist within the structure of any game, he couldn't rely on psychology. He had to prove it mathematically. He had to use high-level topology, completely divorced from human behavior.
And that transition is perfect because we are now entering the absolute deepest, most mathematically dense part of the source material, proving the unprovable. The topological foundations. This is the how of the proof. If he couldn't just point to people doing it, how did he mathematically guarantee that this equilibrium must exist in every finite game ever created?
To understand the magnitude of the mathematical flex Nash pulled off here, we have to revisit that historical anecdote from 1949 that the text mentions. John Nash is a 21-year-old graduate student at Princeton. He walks into the office of John von Neumann, who is essentially the reigning king of the mathematical universe at this point.
Right. And Nash presents his initial existence proof. He shows von Neumann the math, proving that every non-cooperative game has at least one equilibrium point in mixed strategies. And von Neumann's reaction is legendary. He dismisses it entirely. The quote in the text is, "That's trivial. That's just a fixed point theorem."
It sounds incredibly dismissive, almost insulting. But the text provides the context for why von Neumann reacted that way. Von Neumann wasn't dismissing the concept of equilibria. He was dismissing the specific mathematical tool Nash used to prove it.
Kakutani's fixed point theorem.
Yes. The text explains that Kakutani's fixed point theorem was developed by a mathematician named Shizuo Kakutani in 1941 for a very specific reason: to simplify von Neumann's own work. Years prior, von Neumann had written a notoriously dense, agonizingly complicated proof for his minimax theorem. Kakutani came along and showed that you could prove von Neumann's exact same theorem much more elegantly using topological fixed points.
So von Neumann looked at Nash's paper, saw him using Kakutani's theorem, a tool that was basically invented to clean up von Neumann's own messy homework, and he just wasn't impressed. He thought it was a derivative mathematical parlor trick.
He completely missed the forest for the trees. Because while the tool itself, the fixed point theorem, was familiar to von Neumann, Nash's application of it was revolutionary. Nash wasn't just applying it to zero-sum games. He was applying it to all non-cooperative games, regardless of payoff structure.
Yeah.
That was mathematically profound.
Okay, we need to slow down here. The text dives incredibly deep into the topological foundations of these fixed points, and we promise no undefined jargon. So let's start at the absolute bottom. What is a fixed point?
Think of a fixed point as a point of absolute stability within a system of transformations. Mathematically, it is defined as a point x within a set x that remains completely unchanged after you apply a specific function f to it. The equation is simply f of x equals x.
Okay, let me try a physical analogy. Imagine a cup of coffee. I take a spoon and I stir the coffee. The stirring is the function, the transformation. Every molecule of coffee is moving around. A fixed point theorem proves that no matter how aggressively I stir that coffee, there is mathematically guaranteed to be at least one single molecule that ends up in the exact same absolute physical location it was in before I started stirring.
That is an excellent way to visualize it. That molecule is the fixed point. The input location perfectly equals the output location. Proving that such a point must exist within a given system is the primary tool economists use for proving the existence of stable economic systems. The text starts by demonstrating the foundational version of this, Brouwer's fixed point theorem.
Brouwer's theorem. The text says this can be demonstrated in one dimension as a consequence of Bolzano's intermediate value theorem.
Let's avoid Bolzano for a moment.
Good call.
In one dimension, imagine a straight line segment, say from 0 to 1 on a graph. A continuous function maps every point on that line to another point on that line. Because you can't jump off the line, and the function must be an unbroken curve, the graph of that function absolutely must cross the diagonal line where y equals x. The point where it crosses is your fixed point.
Okay, a line is easy to visualize. But a game of strategy with multiple players and mixing boards has dozens of dimensions. How do you prove the coffee molecule exists in higher dimensions? The text introduces algebraic topology here. It talks about fundamental groups and continuous retractions. I struggled heavily with this section. You need to explain this to me like I'm 5.
I can do that. The text uses a brilliant proof by contradiction to explain Brouwer's theorem in 2 dimensions. Let's use a physical object. Imagine a solid flat disk made of rubber, like a solid frisbee. That is our mathematical space.
Okay, I have a solid rubber frisbee.
Now, Brouwer's theorem states that if you stretch, fold, or deform that frisbee in any way, as long as you don't rip it, and you keep it within its original physical boundaries, at least one point will remain in its original location.
The fixed point.
Right. To prove this must be true, the text asks us to imagine that Brouwer is wrong. Imagine there is some magical way to stretch the frisbee where not a single point stays in its original location. Every single point moves somewhere else.
Okay, I'm imagining this hypothetical rule-breaking stretching process.
If this process existed, the text says we could construct a mathematical tool called a continuous retraction. Here's how you build it. You look at a point on the frisbee, you see where it started, x, and you see where the magical stretch moved it to, f of x. You draw a straight line starting from the new location, going perfectly straight through the old location, and continuing outward until it hits the outer boundary edge of the frisbee.
The boundary edge, the outer rim.
Yes. So we've created a mathematical function that takes every single point on the solid frisbee and maps it strictly to a point on its outer rim. It effectively retracts the entire solid disk onto its own outer edge without tearing the rubber.
Okay, I can visualize that. But why does that prove anything?
Because algebraic topology proves that a continuous retraction of a solid disk onto its outer rim is physically and algebraically impossible. It relies on a concept called the fundamental group.
The text mentions homotopy equivalence classes of loops. Please translate.
Think of a rubber band. If you take a rubber band and lay it down flat on the solid part of a rubber frisbee, you can easily shrink that rubber band down to an infinitely small single dot without ever leaving the surface of the frisbee. Because of that property, topologists say the fundamental group of a solid disk is mathematically trivial. The text denotes it with a 0.
The loops can all shrink to 0.
But if you look at only the outer rim of the frisbee, just a skinny hoop around the edge, and you wrap a rubber band around it, well, you cannot shrink that rubber band down to a single point. The hole in the middle prevents it. You could wrap the rubber band around the rim twice or 3 times, but you can never shrink it to 0.
Right, it's stuck around the empty center.
And that's why the text notes that the fundamental group of a hollow circle is not trivial. It is isomorphic to the integers. The text denotes it as z. You classify the loops by how many times they wind around the hole. 1 time, 2 times, -1 time.
Okay, I'm following the rubber bands. How does this disprove the retraction?
If our magical continuous retraction existed, it would require us to smoothly, without ripping anything, transform the complex, unshrinkable loop structure of the outer rim, the integers, completely through the trivial, shrinkable loop structure of the solid disk 0 and back out again.
The text states that this induces an algebraic requirement where the integers must factor through the trivial group 0.
Which is an algebraic impossibility. You cannot squeeze all the infinite complexity of the integers through the absolute nothingness of 0 and get the integers back perfectly on the other side. It's an irresolvable mathematical contradiction.
And because that retraction is mathematically impossible, the original assumption that allowed us to build it must be false. The assumption was, imagine a stretch where no point stays in its original location. That assumption is completely false. Therefore, a stretching process without a fixed point is impossible. A fixed point must exist. Somewhere on that frisbee, f of x must equal x.
Exactly. It is a stunningly elegant proof by contradiction using the abstract shapes of spaces. And this absolute topological certainty is exactly what John Nash leaned on to prove his equilibrium. But he didn't use Brouwer's theorem directly in his first 1950 paper.
Right. The text says he used the Kakutani best response correspondence. How did he take this frisbee logic and apply it to our DJ mixing boards?
He formulated the search for an equilibrium, not as looking for a specific score, but as a search for a fixed point within the player's best responses.
The text defines a correspondence. It says a correspondence is like a function, but instead of mapping an input to a single output, it maps an input to a whole set of valid outputs.
Right. It defines the best response correspondence for player I. It takes all the strategies chosen by everyone else and outputs a set containing every possible mixed strategy on your DJ board that would give you the maximum possible payoff against them.
It gives you a menu of all your optimal moves. And by combining everyone's menus, you get the joint best response correspondence, the master mapping. It takes a specific setup of everyone's mixing boards and outputs the set of everyone's best responses to that setup.
To prove that this massive master mapping has a fixed point, a state where the input strategy is identically equal to the output best response, Nash had to prove that the game satisfied 4 rigorous, non-negotiable mathematical conditions laid out by Kakutani. The text details each one.
Let's walk through these 4 conditions, and please keep grounding them for me. The first condition is the compactness and convexity of the strategy space.
We actually touched on this earlier. The master space containing all possible slider combinations must be a non-empty, compact, and convex subset of a Euclidean space. Let's focus on compact. Compact means the space must be both closed and bounded.
Bounded is easy. Bounded means it doesn't stretch out to infinity. On our mixing board, the sliders can only go from 0 to 100%. They physically cannot go to infinity. It has a strict numerical limit.
Exactly. And closed means the space mathematically contains all of its own outer boundary points.
The boundaries on our mixing board are the pure strategies. Pushing the rock slider all the way to 100% and the others to 0 is the absolute edge of the space. Because pure strategies are explicitly allowed and included in our rules, the space includes its own boundaries. It is closed. So, condition 1 is met. The space is compact and convex. What is the second condition?
Non-emptiness and closed-valuedness. This simply means that no matter what crazy combination of slider the other players choose, you must always have at least one best response available to you. The menu of your best responses can never be entirely empty.
If the menu was empty, the game would break. You'd be paralyzed.
Right. And the text notes that we can mathematically guarantee the menu is never empty by relying on Weierstrass's extreme value theorem.
Weierstrass's extreme value theorem. Again, translating to English, if you have a continuous function operating over a closed and bounded space, that function is mathematically guaranteed to hit an absolute maximum peak somewhere in that space.
Think of it like a topographical map of a mountain range. If the map has a definitive border, so it's bounded, and includes the border edges, so it's closed, there absolutely must be a single highest point of elevation somewhere on that specific map. There is always a peak. Therefore, the set containing your maximizing best responses is never empty. Condition 2 is met.
The third condition Kakutani requires is convex valuedness. This relates back to how we calculate the expected payoff using a linear average.
Yes. The text states that if 2 different mixed strategies are both valid best responses, then any convex combination of them must also be a best response.
Let me make sure I understand this. If strategy option A gives me the maximum possible payout of $10, and strategy option B also gives me the exact same maximum payout of $10.
Then if you decide to just flip a coin to randomly choose between option A and option B, that coin flip strategy itself must also yield an expected payout of $10.
Because it's just a linear blend of 2 identical maximums. Half of 10 plus half of 10 is still 10. This means the menu of my best responses isn't just a scattered collection of isolated dots. It forms a solid, unbroken, convex shape where every possible line drawn between 2 best responses is entirely made up of best responses. The math is smooth. Condition 3 is met.
Which brings us to the fourth, and definitely the most conceptually difficult condition. Upper hemicontinuity, the requirement of having a closed graph.
I stared at this word for 10 minutes. Hemicontinuity. Explain this mechanism to me. What does it actually do?
It dictates how the math must behave at the limits. It prevents sudden, illogical jumps in the system. Imagine you have a sequence of changing input strategies. The other players are slowly sliding their mixing boards inch by inch, converging toward a final limit point.
They're slowly approaching a specific configuration.
And as they slide their boards, your best response menu changes. You have a sequence of corresponding best responses that are also slowly converging toward a limit. Upper hemicontinuity demands that when they finally reach that exact limit point, the limit of your best responses must be a valid best response to the limit of their inputs.
Let me try an analogy. Imagine I am walking toward the edge of a cliff. As I take a step closer to the edge, my best response is to take a slightly smaller step next time so I don't fall. I keep taking smaller and smaller steps as I approach the absolute limit of the cliff. Upper hemicontinuity basically means that when I reach the exact mathematical limit, like, my toes are perfectly on the edge, my best response doesn't suddenly, discontinuously become jump off the cliff. The rule that guided me all the way to the edge must still apply at the edge. The system doesn't magically break or tear just because we reached a boundary.
That is a brilliant way to conceptualize it. Because the underlying utility functions calculating the payoffs are continuous, the best responses behave predictably at the limits. The graph is completely closed. There are no sudden holes in the logic. Condition 4 is met.
This is a spectacular mathematical trap. We've defined this multidimensional space containing every possible strategy, and we've meticulously proven that it is compact, non-empty, convex, and upper hemicontinuous. We have built the perfect cage.
And because all 4 conditions are perfectly satisfied, the trap springs shut. Kakutani's fixed-point theorem mathematically dictates that there absolutely must exist at least one strategy profile where the input into the best response mapping is identically equal to the output.
The strategy is its own best response.
This fixed point implies a state where every single player's strategy is the optimal best response to everyone else's strategy simultaneously. Therefore, no player has any incentive to unilaterally deviate. This fixed point is, by its very definition, a Nash equilibrium. Nash proved it must exist.
It's an impenetrable, airtight proof. But the source text adds a really interesting postscript to this topological section. It notes that in 1951, just a year later, Nash actually published a second, longer paper where he seemingly simplified the whole thing.
Yes, the 1951 Brouwer simplification. Nash realized that Kakutani's correspondences, which map one single point to a whole menu of points, were conceptually difficult for many economists to work with. He wanted a more elegant, direct approach.
So he bypassed the menus entirely. He constructed a continuous function that mapped a single point directly back to a single point. And to do this, he used what the text calls gain functions.
This is a much more intuitive way to think about the equilibrium. Nash defined a formula to calculate a player's positive incentive to change their move. You look at your current mixed strategy on your DJ board. Then, you look at every single pure action you could possibly take. If switching to a pure action would give you a higher expected payoff than your current mix, you calculate that positive gain.
But if switching would give you a lower payoff, the formula just spits out 0. You don't care about moves that make you worse off. You only track the positive temptations.
Precisely. Nash then used these individual gain calculations to define a continuously shifting strategy profile. He built a formula that took your current probabilities, added the calculated gains for the better moves, and then normalized everything by dividing by a scaling factor so the new probability still strictly added up to 100%.
It's a continuous map. You input a strategy, the math calculates all your positive temptations to change, and it outputs a new strategy that leans slightly heavier toward those more profitable actions.
And because it is a continuous, single-valued function, mapping our compact simplex strictly to itself, he didn't need the complexity of Kakutani anymore. He could just use the standard Brouwer fixed-point theorem we discussed with the Frisbee. Brouwer dictates there must exist a point where the input strategy exactly equals the output strategy.
And if the input perfectly equals the output, it means the gain functions didn't alter the probabilities at all. And the only mathematical way the gain functions don't change anything is if every single calculated gain is exactly 0.
Which means there are absolutely no positive temptations to deviate to any other pure strategy.
Which means it's a Nash equilibrium. Proven via a smooth, continuous topological map, it is so mathematically elegant, it feels flawless.
It is flawless mathematics, on paper.
Yeah.
But as we transition into the next major section of our outline, the source text reveals a critical problem. When game theorists took Nash's flawless math and tried to apply it to real-world timelines, they discovered some glaring logical loopholes.
Right. We're moving into the section on refining the rules. Because Nash's original concept assumed a very specific type of game. A static game. It assumes everyone makes their choices simultaneously, in secret, and reveals them all at once.
Like rock, paper, scissors. But life rarely happens simultaneously. Usually, human interaction happens sequentially. I make a move, you see my move, then you make a move. The text calls these dynamic or extensive form games.
And the text points out that in sequential games, the standard Nash equilibrium is too loose, it's too permissive, it predicts multiple possible equilibria, and some of them are deeply, obviously flawed. The main problem the text highlights is the concept of non-credible threats.
Let's explain the mechanism of a non-credible threat. It occurs when a mathematical Nash equilibrium is artificially sustained by a player promising to do something in the future that would actually be highly irrational for them to do when the time comes, but the mere threat of it influences the opponent's current choice.
I have an analogy for this. Let's say I want you to give me your sandwich. I look at you and threaten, if you don't give me your sandwich right now, I will detonate a bomb and blow up this entire city, killing us both.
A bit extreme, but it works mathematically. Let's look at the standard Nash matrix for this.
Yeah.
You giving me the sandwich and me not blowing up the city is technically a stable Nash equilibrium.
Why?
Yeah.
Because if you give me the sandwich, I have my sandwich, and I have no positive incentive to deviate and blow us up, I am stable. And given my threat, you have no incentive to deviate and keep the sandwich because you would rather be hungry than dead. You are stable. The math says this is a valid equilibrium.
But the threat is non-credible. It's hollow. Because if you actually called my bluff and just ate the sandwich, I would be faced with the real decision to actually blow up the city. And since dying is a terrible payoff for me, my strictly rational choice at that future decision node would be to just grumble, do nothing, and stay alive.
Because the standard Nash concept evaluates the game as one giant, holistic block from the very beginning, it allows my empty, suicidal threat to artificially prop up a mathematical equilibrium. It doesn't check to see if my threat makes sense later.
To fix this glaring loophole, game theorists had to develop refinements. They needed stricter mathematical axioms to eliminate these fragile, suboptimal equilibria. The text introduces the first major solution developed by Reinhard Selten, the subgame perfect equilibrium, or SPE.
Selten basically took a sledgehammer to the non-credible threat. He stated that a strategy profile isn't valid if it's just an equilibrium for the whole game. It must also constitute a Nash equilibrium in every single proper subgame within the larger game tree.
It forces strict rationality at every single step of the timeline. In games with perfect information like chess, where you can see the whole board and know exactly what has happened, SPE utilizes a process called backward induction.
Backward induction. Instead of analyzing the game from start to finish, you start at the very end. You look at the very last possible decision node in the game and ask, what is the rational choice here?
Once you determine the rational endgame move, you mathematically lock it in. Then you step backward to the second to last move. You say, knowing exactly what the rational choice will be in the future, what is the rational choice for me to make right now?
You prune the tree from the leaves down to the trunk. By working backward, SPE ensures that rational play is expected at every single decision node, even nodes that are technically off the expected path of play. Returning to my sandwich threat. Backward induction looks at the final node first blowing up the city. It determines that blowing up the city is irrational and deletes it as a valid move. Once the threat is deleted, it steps back to your choice. Knowing I won't blow up the city, your rational choice is to keep your sandwich. The non-credible threat is mathematically erased.
But the text notes that SPE has its own severe limitations. It works beautifully for perfect information. But what happens when there is incomplete or imperfect information? What happens when players are hiding things?
Like poker, I don't know what cards you have.
Exactly. When a game features imperfect information, players don't always know exactly which node they are at in the game tree. They're operating inside an information set. And because of that ambiguity, proper self-contained subgames are rare. This renders the backward induction of SPE mathematically paralyzed.
So how on earth do game theorists mathematically model a game where players are actively bluffing or hiding information?
The text breaks down the next evolution of mathematical refinements. It introduces the perfect Bayesian equilibrium, or PBE, and the sequential equilibrium, developed by David Krebs and Robert Wilson.
Sequential equilibrium. This introduces a concept that feels deeply human: beliefs.
Yes. Instead of just analyzing concrete actions, a PBE introduces mathematical probability distributions over the unknown nodes of an information set. These are formalized beliefs. If I don't know exactly what card you hold, I assign a strict mathematical probability to what I believe you hold, based on your previous actions.
And the refinement requires that my strategies must be sequentially rational given those subjective beliefs. But I can't just arbitrarily believe whatever I want to make the math work, right? There has to be a rule.
There's a strict rule.
Yeah.
The beliefs must be consistently updated using Bayes' rule along the equilibrium path. As new information is revealed through this sequence of play, you mathematically recalculate and update the probability of your beliefs based on conditional probability.
Okay, that makes sense for normal play. But here is where Krebs and Wilson's sequential equilibrium introduces a concept that blew my mind. What happens when someone makes a move that is so wild, so totally irrational, so far off the expected path, that Bayes' rule mathematically breaks? You can't update a belief using Bayes' rule if the probability of the event happening was supposed to be strictly 0. You can't divide by 0.
This is one of the most fascinating mechanisms in game theory, the trembling hand concept. The text details that sequential equilibrium mandates that these off-path beliefs must be mathematically derived as the limit of a sequence of completely mixed strategy profiles.
Let me see if I can translate the trembling hand. Basically, the math breaks if it assumes a human acts perfectly rationally 100% of the time, because humans eventually do something totally stupid. So you are mathematically required to model the stupid move not as a calculated strategy, but as a physical mistake, a tremble.
Exactly. You assume the player fully intended to play their rational, pure strategy, but their hand physically trembled as they made the move, and they accidentally played a disastrously bad strategy with a microscopic probability, like 0.0001%.
It forces the math to account for human error. The text provides a formal limit equation for this, where the sequence of totally mixed strategies and their associated beliefs approach a limit. What does that equation actually accomplish?
It ensures that all players share a common, mathematically consistent belief about the nature and distribution of those off-path mistakes. Even when the game devolves into complete irrational chaos, the mathematical model maintains a strict, logical structure for how to interpret that chaos.
Okay, let's step back and look at what we've done here. We took Nash's beautiful, elegant topological math. We tried to apply it to thinking humans. And to make it work, we had to add subgame perfect equilibria to stop fake threats, and we had to add Bayesian updating to handle bluffing, and we had to invent trembling hand limits just to mathematically excuse human mistakes. It feels exhausting. The more we try to model hyper-rational human cognition, the more tangled and fragile the math gets.
Which is precisely why the next section of our source text provides such a profound paradigm shift. It asks a radical question. What if these trembling hand models show that hyperrationality is a flawed standard to begin with? What if we just remove the thinking part altogether? Do these stable equilibria still exist if no one is consciously doing the math?
We're transitioning from human rationality to biological reality. Evolutionary game theory, survival of the fittest, this is where the must-docs comes in.
In 1973, there was a massive leap in the field. The text introduces the work of evolutionary biologists John Maynard Smith and George R. Price. They looked at the mathematical framework of game theory and realized it could be perfectly, seamlessly applied to evolutionary ecology.
This is a massive shift in perspective. Classical game theory is all about conscious, cognitive agents frantically calculating expected utility in trembling hands. Maynard Smith and Price completely threw the conscious brain in the trash. They replaced thinking humans with unthinking, blind populations of biological organisms.
They introduced a concept called the evolutionarily stable strategy, or ESS. In this biological framework, strategies are no longer conscious choices debated in a boardroom. They are genetically hardwired behavioral phenotypes.
Your genetics dictate your move, and the payoffs are no longer abstract utility points or dollars. The payoff is literal biological fitness. It is reproductive success.
It's a brutal, automated version of Nash's cage. If a genetic strategy has a high payoff in a conflict, that organism survives, reproduces more, and that specific genetic strategy mathematically spreads through the population. If a strategy yields a low payoff, the organism dies, and the strategy is erased from the gene pool.
And the mathematical conditions for a genetic strategy to be classified as an ESS are strictly defined in the text. It imagines a massive established resident population all playing a specific genetic strategy. Then it introduces a small fraction of mutants playing a slightly different strategy.
A mutant invasion. For the resident strategy to be considered truly evolutionarily stable, it must be able to mathematically repel that invasion. How does the text define that repulsion?
It provides two strict mathematical conditions. The first condition checks the initial encounter. The expected biological payoff of the mutant playing against the established resident must be strictly less than the payoff of the resident playing against itself.
Meaning, the mutant performs worse against the established population than the established population performs against its own kind. The mutant is immediately at a survival disadvantage. It gets outcompeted and dies out.
But what if they tie? What if the mutant's genetic strategy is just as effective against the resident as the resident is against itself? What if the mutant can survive the initial encounter?
Then the second mathematical condition acts as a failsafe. If they tie on the first check, then the resident strategy must perform strictly better against the mutant than the mutant performs against itself.
Exactly. Even if the mutant gains a temporary foothold, as soon as mutants start interacting with other mutants, their relative biological fitness drops compared to how the resident handles the mutants. The invasion is mathematically suppressed. The resident population returns to equilibrium.
And the text points out a crucial mathematical relationship here between ESS and John Nash. Every single evolutionarily stable strategy corresponds directly to a Nash equilibrium in a symmetric two-player game. Nature obeys Nash's math.
But And this is a vital distinction the text makes. Not all Nash equilibria are evolutionarily stable.
So an ESS is a strict refinement of Nash. Nature is actually pickier than theoretical mathematics. A strategy might be a mathematically valid Nash equilibrium on a chalkboard, but if it cannot physically survive a mutant invasion in the harsh reality of the physical world, evolution will discard it.
This biological application is incredibly elegant. The text notes that it provided biologists with a massive, highly effective alternative to standard, intensely complicated population genetic models. It allowed them to focus entirely on phenotypic evolution observable physical behaviors without needing to map out the entire underlying genetic architecture.
And the text gives us these vivid, real-world ecological examples of this mathematical game theory playing out in the wild. We finally get to talk about the oryx and the muskox.
These animal examples perfectly illustrate the tension between different biological strategies. The text frames their behavior using classic game theory archetypes, the dove strategy versus the hawk strategy.
Let's start with the oryx. The oryx is this large antelope, and it has these incredibly sharp, long, pointed horns. Biologically, they're lethal weapons. If they wanted to, they could easily impale each other during conflicts over territory or mating rights, but the text notes they adopt a stable dove strategy.
When two male oryx conflict, they don't try to kill each other. They restrict their physical interactions to highly ritualized, non-lethal displays. They clash their horns together, but they intentionally, genetically avoid lethal strikes to the body. It's a cooperative, mutually beneficial equilibrium that preserves the population.
But then you look at the muskox. They adopt the absolute extreme hawk strategy. When male muskox in conflict over mates, there is no ritual. It is a violent, full-speed, catastrophic headbutting contest. They crash their skulls into each other with massive traumatic force.
And the biological cost of this hawk strategy is severe. The text explicitly states that up to 10% of adult male muskoxen die annually from injuries sustained in these conflicts.
10%. That is a massive, seemingly completely irrational mortality rate just for the right to mate. If the oryx can figure out how to settle disputes without dying, why does the muskox accept a 10% death rate? It seems mathematically foolish.
From an individual survival standpoint, it might seem foolish, but the text notes that this biological divergence illustrates how different environmental and social contexts fundamentally shift the mathematical fitness landscapes. You have to calculate the expected payoff based on the environment. For the muskox, living in their specific, incredibly harsh Arctic environment, the evolutionary payoff, the absolute necessity of securing a mate and passing on genes is so overwhelmingly high that it mathematically justifies the 10% risk of death.
The expected utility of mating is worth the risk of dying. Therefore, the brutal hawk strategy is a mathematically sound, evolutionarily stable strategy for the muskox, even though it's bloody. While the peaceful dove strategy is the ESS for the oryx. The unthinking, unfeeling process of biological evolution flawlessly calculates the equilibrium based on the environmental stakes.
It mathematically finds the topological fixed point through trial, error, and extinction.
Which brings us to the final, and perhaps most mind-bending section of our deep dive, the algorithmic catch. We've established a lot so far. We know these equilibria absolutely exist in abstract topological space. We know they exist in complex human behavioral games, even if they require trembling hands to model perfectly, and we know they dictate the physical survival of species in the wild.
They are everywhere.
Right. So if we know they exist and we mathematically understand the blueprints, we should just be able to program a computer to find the exact Nash equilibrium for any complex scenario. Right? I should be able to give a supercomputer the payoff matrix for a complex market economy, and it should just calculate the exact optimal stable strategy.
That is exactly what computer scientists assumed for decades. But when they actually tried to build the algorithmic code to calculate it, they hit a massive, seemingly impenetrable brick wall. And the reason goes all the way back to the topological proofs we discussed earlier with the rubber frisbee.
Brouwer and Kakutani.
Yes. The text clarifies a crucial defining limitation of those topological proofs. They are fundamentally non-constructive proofs.
Non-constructive,
Right.
Meaning they mathematically guarantee the equilibrium is absolutely 100% inside the room, but they don't give you a map or a flashlight or any set of instructions on how to actually find where it is hiding in the room.
They offer absolute proof of existence without offering a search algorithm. And this massive algorithmic gap, knowing it's there but not knowing how to find it, became one of the central agonizing questions in theoretical computer science. The text poses the question directly. How long does it actually take for strategic agents to mathematically converge to a Nash equilibrium, and can it be calculated in polynomial time?
Okay, we need to carefully unpack the computational complexity paradigm here. When computer scientists talk about how hard a math problem is for a computer to solve, they usually use the P versus NP paradigm. Explain this mechanism to me. What makes a problem NP?
P represents problems that a computer can solve relatively quickly and efficiently in what's called polynomial time. NP represents a class of problems where, if someone hands you the correct answer, you can quickly verify that it's correct. But finding that answer from scratch might take an astronomically, impossibly long time.
The classic analogy is a massive Sudoku puzzle. If the grid is empty, solving it from scratch is incredibly hard and time-consuming. But if someone hands you a completed grid, checking to make sure there are no duplicate numbers in any row takes 2 seconds. That's NP.
Exactly. And the absolute hardest problems within that NP class are called NP complete or NP hard. The text points out a vital distinction here. If a typical problem is classified as NP hard, its immense difficulty usually stems from the terrifying possibility that a valid solution might not exist at all. The computer has to painstakingly search every single possible path, every dead end, just to eventually confirm that there is no answer.
The search space is exhaustive, because the answer might be no. But this raises a massive logical problem for our topic. How do you classify the computational difficulty of finding a Nash equilibrium? The mathematical problem of computing a Nash equilibrium, which the text denotes as Nash in all caps, is fundamentally different from a standard NP problem.
It is entirely different precisely because of John Nash's topological proof. Nash already mathematically proved, without a shadow of a doubt, that a mixed strategy equilibrium always exists in every finite game.
The decision problem, does a solution exist, is utterly trivial here. The answer is literally always yes. The computer never has to worry that it's searching for something that doesn't exist.
Consequently, the text states a major tenet of complexity theory. The Nash problem cannot be NP complete in the traditional sense unless the entire overarching paradigm of NP equals co-NP is true, which theoretical computer scientists widely believe to be false.
So it's a guaranteed needle in a mathematically infinite haystack. You know for a mathematical fact the needle is in there, but traditional computer science complexity theory didn't have an accurate category to describe exactly how hard it is to blindly search for it.
Until the 2006 breakthrough. The text highlights a monumental field-defining paper published by Konstantinos Daskalakis, Paul Goldberg, and Christos Papadimitriou, alongside independent but related work by Shi Chen and Jody Deng.
What exactly did they prove that finally solved this?
They proved that the computational problem of finding a mixed Nash equilibrium in a game is PPE complete.
PPD complete. That is a very specific, highly niche class of computational complexity.
PPAD stands for polynomial parity arguments on directed graphs, but you don't need to memorize the acronym. What you need to understand is the mechanism of why it is so difficult. The text explains that their proof established a direct, unbreakable computational equivalence between finding a Nash equilibrium and finding a Brouwer fixed point.
They proved that the exact mathematical mechanism that guarantees the equilibrium exists, the topological fixed point on our rubber frisbee, is the exact same mechanism that makes it computationally intractable for an algorithm to find.
Yes, think of it like a maze. A PPD problem is like being dropped into a massive, incredibly complex maze. The topological rules of the maze mathematically guarantee that, because of how the walls are drawn, a specific exit absolutely must exist. But the rules don't give you a map.
So the only way for the algorithm to find the exit is to physically trace every single hallway, hit every single dead end, and backtrack over and over again until it blindly stumbles into the exit.
Precisely. The search pathway is fundamentally mathematically inefficient. There are no shortcuts.
So what does this actually mean for us? For economists trying to predict markets, or programmers trying to build AI that negotiates?
It means that even for relatively simple games, with just a few players and a few variables, it can take mathematically unreasonable astronomical amounts of time for an algorithm to find the exact mixed Nash equilibrium. It implies a profound limit on our computational power. We can prove the stability exists, but we are mathematically blind when trying to calculate exactly where it is.
It is an incredible, almost poetic paradox to end on. John Nash, as a 21-year-old student, gave us the universal, unbreakable blueprint for strategic stability. He used high-level topology to prove that this stability absolutely must exist everywhere, in every game. But the world's most advanced computer scientists proved that, practically speaking, finding it mathematically is often physically impossible.
It perfectly frames the limits of human calculation. Let's pull all these threads together for you, the listener, as we wrap up this deep dive into Nash's universe. We started in the paranoid zero-sum cage built by von Neumann. We saw how Nash shattered that cage by introducing the reality of strategic independence and the concept of probabilistic mixed strategies.
We explored how he proved that stability always exists, using the topological magic of Kakutani and Brouwer's fixed points, proving that the math never breaks at the limits. We saw how game theorists desperately tried to refine those rules with subgame perfection and trembling hands just to account for human bluffs and human stupidity.
And we saw how evolutionary biology adopted that exact same mathematics to explain the brutal physical realities of the oryx and the musk ox, before finally hitting the absolute brick wall of theoretical computer science, realizing that calculating these equilibria algorithmically is PP complete.
And why should you care about all this incredibly dense math? Because anytime you are negotiating a salary with a boss, anytime you observe animal behavior in a nature documentary, or anytime you watch complex algorithmic trading bots interact in a financial marketplace, you are actively witnessing the invisible mathematical architecture of the Nash Equilibrium trying to find its stability. It is the hidden universal operating system of all strategic interaction.
I want to leave you with one final, slightly provocative thought to chew on. Something that wasn't explicitly spelled out in the source text, but builds directly on the tension we just explored.
What is it?
We just spent the last 20 minutes establishing that computing a Nash equilibrium mathematically is PPA complete. Our most advanced computer science, using our most advanced silicon supercomputers, dictates that finding these fixed points algorithmically is a fundamentally broken, inefficient search that takes unreasonable amounts of time.
Right. The algorithmic search is inherently flawed and practically impossible.
But we also just established in the biology section that evolution flawlessly finds evolutionarily stable strategies, which are strict Nash equilibria all the time in the real world. The oryx found its fixed point, the muskox found its fixed point. The environment calculates it.
It does. Nature finds the equilibrium.
So, if nature effortlessly finds stable Nash equilibria in the physical world through the raw, unthinking trial and error of survival, but our most advanced mathematical algorithms prove that calculating these equilibria on a computer is PPAD complete and practically impossible, does that mean the blind, unthinking, chaotic process of biological evolution is inherently a better, vastly more efficient computer than anything human logic can ever build?
That is a staggering tension. The messy physical world effortlessly solves the very mathematics that our pristine silicon computers choke on.
Just something for you to mull over the next time you see a flock of birds flying in perfect formation, or watch a complex economic market unexpectedly shift and settle. That underlying structural blueprint might look chaotic to us, but it always inevitably finds its perfect mathematical balance. Thank you for sharing these incredibly dense, fascinating sources with us, and thank you for joining us on this deep dive.